It's my pleasure to sit on stage with Nick McKeown, who is one of those people who needs no introduction, but I wanted to find a way to introduce him. So I thought I'd go back to the beginning. So I think we crossed paths, although unaware of it, back in the late 80s at HP Labs Bristol, which is where you got your start.
Right.
So it'd be interesting to hear how you got from HP Labs Bristol to where you are today. But he was working on network interface cards, maybe, or it was network communication?
The very first FDDI, 100 megabit per second network interface card.
Right, and I was working on
it was about this long.
Yeah, the one we had was about that big. Yeah, we had been using that. Anyway, so obviously Nick's been involved with SDN and P4 and this whole programmable networks for quite some time now, but I wanted to give you a chance to tell us what you're doing now.
Okay. What am I doing now? Apart from sitting talking to you, Larry. Thank you. Great to be here. Since middle of 2021, I've been at Intel, as somebody may know, where we're sitting right now, although across the street from here. When Pat Gelsinger returned to be CEO at Intel in the beginning of 2021, he was pretty determined to establish a network and edge computing business that was distinct from the very successful server and client businesses. But as you know, Intel was in a tough time, right? It needed a big turnaround. An iconic Silicon Valley company that had stumbled, lost its way, both on strategy, investment, and execution. So he invited a number of people, myself, Greg Lavender, who was CTO at VMware at the time, to come and really help be part of that leadership team. So it was a very challenging but exciting thing to try and take on. And through the investment in manufacturing that you've probably seen, biggest investment in world history in manufacturing, and also in turning the Xeon franchise around, now more successfully so with the Sapphire Rapids launch at the beginning of this year. Intel it takes a long time to turn that big ship around, but having a seat at that table was a bit too exciting to turn down. And so that's what I've been doing for the last couple of years.
Great. So, I mean, you were clearly involved very early on in P4, and that naturally followed from your earlier work on SDN, that you hit a roadblock and we got to program the data plane, and then P4 became a thing, and you started to evangelize that and take it into Barefoot, start a company, a startup company. That company was acquired by Intel. You end up at Intel, so I'm trying to trace the path here of where P4 has been and where it's headed. Yeah. And then you found yourself having to make decisions about the future of a switching chip there.
Yep.
Talk about that.
Yeah. So P4 started in my recollections. It started in about 2012, 2013. I was just talking to someone about Istanbul. I remember I was actually sitting in Istanbul in 2013 when Amin Vedat, Jen Rexford, Dave Walker, and a few of us were really trying to figure out what the heck should we call this language that we've been discussing for a while. We felt that there needed to be a way to describe or specify, as Rob was talking about earlier, specify a forwarding behavior in a way that was unambiguous, and that the time was overdue. Kind of regardless of Tofino and Barefoot, you just needed one because the kind of the world and networking industry was lacking such a means to specify forwarding behavior. I was sitting there thinking, what do we call this? And I suggested as a joke this name that I assumed that would be thrown out because it sounded too much like B4, the Google network. And before I knew it, everyone else said, oh, that's a good idea. So I had to bite my tongue, and then P4, the name stuck, and that's where we are today. But what followed after that was a quick bringing together of a number of people who kind of felt the same way, and they weren't all interested in switching. They were interested in the means to specify forwarding behavior in the kernel, in FPGAs, in switches, and sometimes it was just to have an unambiguous means of specification. To be able to say, this is a behavior I want, that was distinct and abstracted away from how it was implemented. A bit like when we write in a high-level language, abstracted away from the object code or the executable that's running on the machine. And so a lot of debate took place about how to to do that, and several of you are in the room today who were part of that debate and discussion that led to sort of figuring out how you have that unambiguous specification. Now, it was fortuitous, and for me personally, it was driven by the need to have such a language, because if you're going to build a Tofino programmable switch, you need a language to program it in. And the goal was to establish something that was independent of Tofino, that wasn't tied too much to Tofino. As you know, that's hard, right? Because things like resource limitations, the specifics of the pipeline, it's hard to make sure they don't become entangled with the language. But a lot of very, very sort of sincere and effort and energy went into trying to make that as separate as possible so that you could have other P4 programmable targets, whether they are SmartNICs or FPGAs with particular internal structures, and that it would lend itself to code that would be generated for the kernel or for user space as well. Now, over the next few years, it was really a question of how do you bring together and keep together a number of different sort of separate interests. And I assume this must be the case in generating any new language, creating any language, whether it's for digital signal processing, for graphics, for a general purpose compute. Different people have different plans, different aspirations with it. Now, it turned out that the first dedicated target that was running at line rate was the Tofino switch. And to be honest, it got a little too coupled early on, and then with P416, we tried to make sure that it was a little bit more decoupled, because if the language is to be successful, languages ideally live longer than chips and particular products, then we needed that to happen. But to get to the rest of your question about, okay, well, then what happened? Before got acquired by Intel in 2019 after the first two generations, Tofino 1 and Tofino 2, the 6 and the 12 terabit per second switches were just coming onto the market. Well, the 6 had been on the market for a while, the 12 was on the market. And so then an economic downturn hit. And you're probably all wondering, so, you know, what happened? What did Intel go through? What was the big deal? It's super simple. It's super simple. Today, to design and manufacture a chip, it's about $200 million. Whether you're a startup, whether you're a big company, Barefoot spent about $200 million. Pensando spent about $200 million, I believe. Everybody spends about $200 million on a new chip. And from where we were with the economic downturn, you just have to, at the end of the day, run a business and look at it hard and say, how much do you invest? What is the return you get on that investment? You rank order the various programs that you have within the network and edge business at Intel. It's about $10 billion worth of business. And then you rank order all of that and say, where are you actually expecting within the horizon? And when those downturns hit, it forces you to make decisions that you would not make if there wasn't a downturn. If there hadn't been that downturn, we probably wouldn't be having this fireside chat today because it wouldn't have been necessary. So in a way, it's kind of a straightforward business decision. It doesn't make it any easier, but it's an essential and an important decision to make. So what we actually decided to do was to continue with the Tofino 1 and Tofino 2. And the Tofino 1 and Tofino 2 are in a number of products in the US, in China, and in Europe. And as a consequence, we wanted to make sure that we would continue to support those. They're still available, they're still supported. There is no end-of-life plan, there is no end-of-support plan. They will continue so long as people want to buy them. And at 12.8 terabits per second, Tofino 2 is expected to have quite a long future. Tofino 3, which you may or may not know about, was going to be the next one. Would have been the next product at 25, and then there were more beyond that we hadn't talked about. And so we just decided we couldn't afford that future development based on the current economy. That's it. It wasn't any more complicated than that.
Thanks. So I've got another question or two for you, but I wanted to say that we're planning to spend most of the session with you folks at the mics here, so please feel free to start queuing up at any time and ask your questions. But I'm going to follow that up with a bit of ruminating that I have heard almost immediately after the announcement. Everyone in the academic community was going, oh my God, we've got PhD students who were planning to do work on Tofino. Should they jump ship? Should they do something else? Is this still a viable, and P4 is a programming language, as you pointed out, it should be independent of chips, but there's a linkage there because, as a PhD student or as a researcher, you like your research to have impact, and so you want to see that there is a future there. So what would you say to that PhD student?
So I think the first thing to do is to take a step back and say, why did we need a programming language in the first place? Right? Where were we in 2012 or so that made us think about doing this? It was because we'd just gone through a transition in the networking industry from fixed, vertically integrated, and frankly, not particularly well engineered routing and networking equipment that didn't have the scrutiny of open interfaces and the ability to be able to pick and choose. The networking industry had been held hostage for a long time and said enough is enough. And so the networking equipment industry responded by breaking apart some of those interfaces. I actually think it would have happened if the term SDN had never come along or the term OpenFlow had never come along. I think the pressure was so strong, particularly in the cloud service providers. Okay, so now you've got open interfaces. You've got open interfaces down to the forwarding plane. In an environment where there was one very, very dominant equipment manufacturer and one very dominant semiconductor manufacturer. Right? And those things are not particularly stable long-term, or they tend not to be stable long-term. They tend to change over time. And it's usually changes like this that bring about that change. So we have gone through this transformation where open interface down to the switching, and you probably remember some of the things, the descriptions that were SAI and et cetera that were going on at that time. The general view was, or our view was, rather than it being fixed, like OpenFlow or a fixed interface, it would allow a much greater path for innovation. If it was programmable, then the programmer can program and decide the behavior that they want. You all know about that. And it would make it clear to the silicon manufacturer, the switch manufacturer, or whatever the target was, what to do as well. That's to build the best damn programmable device that you can. A little bit like with CPUs, very competitive, right? Duking it out over who can build the best CPUs, who can build the best GPUs, et cetera, right? That's how that goes. Could we create that similar environment rather than lock in? I find that very cynical, right? Locking in interfaces, locking in APIs, locking in. That's just a sign that you know that you don't have the best product. Right? So could we force that to be more open and in the hands of whoever was owning and operating the network? That need still exists today. It exists for NICs, for switches, for almost any kind of networking equipment. If, as a community, we can make sure that those devices, that forwarding plane, is programmable, it moves the entire networking industry forward because it allows those who own and operate networks, those who understand the problems that they're trying to solve the best, to decide for themselves how packets are processed. Because if you don't control how packets are processed, you're not in control of the network, right? You're just reliant on some standard that was created 20 years ago by a committee. But if you can turn that into a software problem, like we've turned much of the rest of the industry, then you're in charge. You all know that, otherwise you wouldn't be sitting here today. But that job still exists, that need still exists. Is just that it's moved. I was wrong. The place to do this is not primarily in switching. The place to do this is in the NICs. Some people call them the smart NICs, Intel calls them IPUs. What is an IPU? An IPU is a fast programmable packet pipeline coupled with some CPU cores. There are several alternatives to this on the market, as you know, whether they're FPGA or ASIC based, and Intel has both. Why is it that that's going along healthily and the switching didn't? Well, it's very simple. Every server has an IPU, or a NIC or a smart NIC. You have one switch for every 48 servers. It's a lot smaller market. That's it. Now, for the SmartNICs and that programmable device that sits on each server, it is also closer to the kernel and the applications and the developer. And in most companies, most cloud service providers, it's where they're going to program. All right? It's much, much easier. It's much more familiar rather than this switch, which is further away. In my mind, eventually, both will be programmable. Because unless you control the entire forwarding pipeline, you're not in control of the network. But if you're looking from a business, through a business lens of where the big volume is, then the big volume is clearly on the 1%.
So do you think you had to do the switch first? I mean, we've been fighting over SmartNICs and how to program them for as long as I can remember, probably back to those FDI days. Maybe you have to put that flag out there. I don't know. Sometimes it's the thing that you needed to do. You needed to do the thing beyond it to get there.
Yeah.
I don't know.
So one thing that, so in 2010, when we started working between Stanford and TI on what became the Tofino product, it was originally had a different name, and as some of you know, was published at around about that time. The conventional wisdom was still very much, you couldn't build a programmable device that had the same power, performance, and area. You still hear people say this. I mean, talk about complete blindness, right? In 2016, in January of 2016, there were 2 chips on the market that were available and in customers' hands almost exactly at the same time. There was Tofino 1 at 6.5 terabits per second, and there was an alternative at 6.4 terabits per second that was fixed function at the same time. If you put the dies over each other, they were the same size. That tells you they're the same area. That tells you they're the same cost, because that determines the cost. They had the same performance. They had this, and one was programmable and one was fixed function. What that tells you is there is no compromise. And actually, after you look at it for a while, you realize, of course there isn't a compromise, because the majority of a switching chip is around the I/O. 30% is on the I/O. That's the same whether it's fixed or programmable. Then there are the lookup tables and the memory for the packet buffer. They're the same whether it's fixed or programmable. You've got about 10-15% of the chip left that determines whether it's fixed function or programmable. 10 to 15%. And it turns out that in modern stack-ups, metal stack-ups in silicon, actually most of that actually disappears in terms of the way that you route the chip. So there was nothing magical. It was just merely making the observation that this conventional wisdom was wrong. I always like that quote. What is it? I think it was from Leonard Cohen. For those of you who remember him, everything has a crack in it. That's what lets the light in. And so the thing here was, there was this conventional wisdom. There are so many conventional wisdoms in our field in networking, right? And when you sort of turn them over a little bit and you say, that's a crock. That actually doesn't hold whatever. I love those. They're fun to find. So this was just an example. So I think in answer to your question, you had to sort of say, let's put a stake in the ground and say, for the most challenging device, that switching chip, you can do it so that it has the same power, performance, and area as the fixed function. If you can do it that, you can do it for anything. So it should, hopefully, give confidence whether you're building a SmartNIC, IPU-style product, or some other kind of product to say, if I'm careful, doesn't mean you can be complacent. If you're careful, you don't have to take a compromise on the power or the performance or the cost.
Yeah, that's good. So I'm going to let there be an awkward silence waiting for someone to come ask a question, because that's the only way to get someone to come ask a question.
Otherwise, you've got 2 professors here that are going to sit here, and when there's silence, we always talk nonstop forever.
Surely you have a question. All right, good.
Hi, it's Bill again from Polytechnique Montreal. We have a Keynote NSERC researcher in P4 programming with Intel as one of our industrial partners, Noviflow and Calum, everybody in the field. And where I'm going with this, I was thinking, as you said, if I got it correct, what Nick was saying is, even though Tofino 3 was in the process, because I read a white paper with a Baidu being part of your thing, but you say you stopped it. It's not going to be Tofino 3. Is that what I get out of you? it's going to be Tofino 1 and 2, but not the 3 because the economics were not there.
We discontinued to
Yeah,
3.
okay,
so
that's
that
what I
will
got.
not be a product.
And now you say that because, again, of the economics, that the programmable NICs are the way to go. Because
No.
they...
It's not because of the economics that the... Oh, I'm sorry, let me finish your question. I want to...
No, that was the thing. I was just to say, like, because now it seems that we're changing, okay, P4 language is going to be there, but we're changing basically where we apply the P4 language. Like, let's now move it to the PNAs or something like that, programmable NICs.
So there are at least 2 commercial products deployed today that have P4 programmable pipelines in a smart NIC.
Yeah.
There are probably more that I don't know about. Actually, I can think of at least 3, right, that have both ASIC and FPGA, right? So it actually has already happened, and there are far, far more deployed P4 programmable pipelines in SmartNIC IPU style products already today than there ever were with switches. Now, there is a derivative languages of P4, so P4.16 that we all know and love and sometimes hate. The P4, there was the P4.14 that that was spun off into or derived into what I think is called NetPL. So there's another language that is used for programming switches. So there are a number of devices out there already today. So I think what you have to do is to separate the language from the devices, right? Just, as I say, if it wasn't for an economic downturn, we wouldn't be having the conversation. That actually says nothing about whether programmable, whether it's smart NICs or switches.
It's just it seems
are going to be around
targeting
in the
different kind of devices now. Like, it seems
I mean, I think they would have happened anyway, and I think they would have actually swamped in volume regardless. There are a lot more of those devices. Every cloud service provider is on a path to having widely deployed smart NICs that are programmable. Many of them, in fact, almost certainly the majority, will be P4 programmable, whether they come from Intel or somebody else. Right? That's just sort of inevitable, I think, regardless.
I have another second part of question, because you said like the Tofino 1 and the Tofino 2, you're going to continue supporting it. There's no
That's correct.
update.
Yeah.
However, let's say another competitor comes in and introduces something new, and already there's something from Juniper, the Trio chip, that say, we can do something more with stateful stuff, maybe if we have a main memory. So let's say something becomes, and I don't know, it gets more adoption, and they're starting taking the market away from Intel. Would that all of a sudden say, hey, the economics is not there anymore, maybe we should stop also supporting Tofino 1, Tofino 2?
Like anything, if people buy, you build and sell.
Okay,
and if people stop buying, then you start building and selling, right? It's just that's business as all businesses have to work. I'm sure yours, I'm sure yours too. But in terms of will P4 over time be replaced by a different language, by a different approach? If there is a better one, then of course, and that's how it should be.
Yeah, exactly.
Right? It shouldn't just sit on its laurels and say, hey, we're the best. No, of course not. You actually got to keep moving and improving and saying, hey, the needs and the requirements change over time. It's the nature of our industry. I would just come back to saying the fundamental need and problem of, if you own a big network, you're a cloud service provider, you're a communication service provider, you've got tens of thousands of switches and hundreds of thousands of servers with NICs attached. If you want to be in charge of how that works, if you want to control how that works and determine for yourself, you need it to be programmable.
Yes.
Right? They are choosing with their feet to predominantly go to the servers, the NICs, and the smart NICs for now. They know better than we do, right? They certainly know better than I do. If that's what they think is the biggest problem to solve, then I respect that.
Yeah, it makes sense. Yeah. Right, thanks.
Thank you.
I'll let Aaron ask first, because I get to talk to you all the time. But. All right, I guess that's fair. Hi.
Hello.
I was curious what you might find or think would be most impactful to continue adoption or even accelerate adoption of P4 or programmable data planes in general. What type of tooling do you think is missing or would be great for folks to focus on to increase adoption and maybe sell some more Tofinos?
Yeah. The thing that I think there are many paths to take. So if we take in terms of the developer tool chain, what do we have? We have, for the first time, an unambiguous way of specifying behavior. fact, once you've looked at or written or read P4 programs and you go back and read IETF RFCs, they're kind of funny. Because you read and say, oh my gosh, that is ambiguous. Not surprising that for years and years there've been interoperability. Think how much gets spent on interoperability. If both products were checkable against a P4 specification, if it was only used as a way of specifying behavior, even if they chose to implement it in fixed function, if that represented the behavior, you could save a fortune, both in terms of the lab size, the deployments, the time, in order to be able to bring these together. So there is a big missing piece, which is to say, how do we make that happen? Well, of course, we need to demonstrate, I don't think you could enforce, but demonstrate to those who buy equipment the value of specifying that. Some do already, and so in case of some Tofino-based switches, the customer had said, here's the P4 program. That's what we're going to test it against when you bring it to us. Because there's a long time of validation and whatever in order to be able to demonstrate that it meets their needs. And so they were telling you, this is our need. And it's a very powerful tool in the hands of the cloud service provider, the big enterprise owner, whoever it is that's building the product that uses it. So what else do they need? Well, if they've got that, how do they know it's correct? How do they know their specification is correct? Just think of the work that's been done, because now you've got an unambiguous language in terms of verification or testing that against required behaviors. So, the work that Nate Foster and others have done along these lines is super powerful. This was never possible before in any practical way. So those, in terms of tool chains, Intel have produced some tools for visualization for the internal workings of the chip. Have you ever seen the internal workings of a chip before that? Never, right? Why would you do that? It's fixed function. You don't need to show what the insides looks like. If you've got a programmable device, you need to in order to help people to design a program that works and fits in order to do that, just like we used to with GDB and things like that. So it allows you to have that tool chain. So that whole tool chain is waiting to be created. And then there's another one, which is between the SmartNICs, the IPUs, and the kernel. Right? So today we've got this situation where if you're in user space, you're using DPDK probably, and if you're in the kernel, you're using ePPF, and if you're trying to accelerate the hardware, you're using P4. It's like, how do I do all of this? There is one, probably 5 PhD theses ready to be written that says, how do I solve that problem? How do I put myself in the shoes of that developer and say, how do I bring all of those together in a meaningful way that makes it easy and thoughtful? Because if I needed to run in accelerated hardware, I need a language like P4. But that's harder to use than DPDK, right? And ePPF fits somewhere in the middle. So how do you bring all of these things together? So I think in terms of the tools and the development chain, there's a massive amount to be done that's independent of whether the switch is programmable.
Right. Thank you very much.
Thank you. Rob.
So a question that kind of keeps me up at night that I'll throw out to you, and maybe it'll generate some interesting discussion, is a lot of blood, sweat, and tears went into trying to make OpenFlow go. And I feel like OpenFlow superficially was a bit of a failure. It's not the thing that's driving our network right now, but it's had a great secondary impact, and I think it's kind of unlocked a bunch of stuff here. And I agree with what you said, that I think even without OpenFlow, we might be here, but it might take a couple more years. And I think, take the Tofino chip, similar trajectory. Like we are where we are right now commercially, but it's had a clear impact on the industry. Some of that logic has ended up in smart chips and whatnot, and it's certainly impacted competitors. And the question is, can you think in retrospect of how we could have gotten here more efficiently? and like, it's still not clear to me. And so, I don't know, I'll throw that over to you.
Good question.
That's great. The networking industry, as you know, is one of the most closed-minded, and stuck businesses in all of IT, right? The telco industry, and still the sort of the equipment industry. It's better than it was, right? Because the power is with a very small number of players who have chosen to keep it locked, right? And then work actively against. If you step back and say, how could they sleep at night? Right? How could they sleep at night? I couldn't do that. Right? But what is our job then? Our job is, and you may have seen me use slides like this before. Take a piece of equipment, you've got a big chisel and a big mallet, and go smack into the side and open it up, and open up the interfaces. I think that's a job. And I particularly think as a professor at Stanford, that was my job, right, to do that. And you were part of that too when we were trying to do that with OpenFlow. It isn't that you know what's going to happen. You just say, we're going to shake things up, bang, and then see what happens. In some ways, OpenFlow lived on for, I mean, there's still one big cloud service provider that has it very largely installed in their environment, because it was simple and fixed and sort of cheap and cheerful way of doing it. I actually don't know of a better way, because the poo-pooing of the industry is so loud and so sneering and so resistant to change that I think we just have to, and we're just a small team of renegades, right, that we have to be able to just sort of shout loud. And the way to shout loud is to sort of create a lot of noise around a particular way of doing it and say, this may not be exactly right, but it's something like this. Right.
I asked that at the P4 conference for a reason, so thank you for the answer.
Thank you. So please keep being renegades.
Nick, I have a tricky question. I remember your first expose presentation, yes, in Intel, when you joined Intel, yes. And this presentation, yes, you told that the future of the P4 is the do-it-yourself protocol, yes, in your data center, yes.
Yeah.
The first question is, does it happen, or do you see this one? And the second question is, where do you see a future? What networking problem should be, let me say, better defined by the P4 or maybe some other languages? Yes.
Yeah. So I always like to go back to the example, which was partly what prompted P4 in the first place. And it was in the early days of network virtualization in data centers. And Cisco and VMware defined a particular way of doing the virtualization, right? And then said, yep, we're ready to go. This is the way. We'll do all the software to do it. And then it was 4 years before a chip came out. Had that been programmable, it would have been a few months, right? It would have been moving at the same pace. And so the thing that's actually slowing us back is any insistence to make something fixed function. Because if you want different layers of processing, different protocol stacks, think of segment routings, SRv6, for example, right? How do you do that when you've got a fixed function device that doesn't know how to read that number of labels? Something is programmable and it needs the resources to do it, then you've suddenly got a way in order to be able to do that. So programmability, we all know this, is that path to innovation. In order for the networking, for the low-level networking and packet processing to be innovating quickly and for there to be a continued fast pace of innovation, we have no other choice. We have to do that. It's only a question of time. And so the dam will break up, will build up again, and it'll break, and then we'll have, it'll be back. In the meantime, you can do a huge amount by doing it at the edge in the SmartNIC or IPU, and then encapsulating through the network. So you say to the network, I'm going to pretend to you that nothing changed by putting some encapsulation around it, the U network, U fixed function network. That's a compromise, but that compromise works for many people sufficiently, and at some time that will break down. If you want to instrument on the switch itself, think about in-band network telemetry, for example. That couldn't have come about had you not had programmable switches. Because it's not because it's difficult to instrument something, it's difficult to know where to put the information. Every network wants to put it in a different place. If it's fixed function, you've got to support all of them from day one. Not possible. If it's programmable, then you can put it in wherever makes sense for that network. So it gives you that flexibility and that freedom. For now, I think almost all of that effort will go into new congestion control mechanisms, new ways to do instrumentation and telemetry, new ways to figure out how to dissect things for machine learning training. Those will tend to happen in the SmartNIC and IPU for now. And then the shortfall on the switch will become clear again, and so we'll go back to trying to do it there, I'm sure.
Do you think that maybe the next level of the P4, for example, for the stateful processing will be required, or that we can do this using the current P4 definition? Yes.
So it's interesting that we always talk as if somehow P4 and stateful are in opposition, and I never quite understand that, because there's a lot that you can do and express with the P4 language and through P4 extensions that you can do for the stateful processing. Would it be better with more? Hey, if there can be agreement about what, absolutely. There just needs to be agreement. It's a language that's held and maintained by an open source group.
Thank you.
Thank you.
Nick, back to the question of switch versus
Yeah, yeah.
NIC.
Yeah.
So how much do you think the success of P4 or programmability in general is limited by lack of feature pressure on the switch versus NIC? There's, every day you can imagine a new thing that you could do.
Yeah. I mean, it already is largely dictated by feature pressure from the NICs, right? And that's how it should be, because there are a lot more of them than there are of switches. So I imagine that will continue. The language should adapt for where it feels the pressure from where it's going to be useful. It should. There's no need for any religion here. Religion is actually unhelpful completely in terms of, from a P4 perspective. If we all put our P4 hats on, then the more targets, the better the targets, right? And I would love it. I always used to say to the Barefoot team, and I've said it publicly too, if there was ever a better, more programmable switch than Tofino, then it should win the market, and we should be ashamed of ourselves, right? Let the best one win. It's about creating a level playing field for targets. That's how our industry should be.
Right.
Our industry would be so much better if you have a level playing field, and that's beginning to evolve more in the smart NIC and IPU space, right?
But will we ever see enough feature pressure on the switch side? Or
I mean, I think the sign that we see is that there's less. There is quite a bit if you want to do congestion control. Most of the new congestion control mechanisms that are used inside data centers, they either rely on signaling that they can create from this, or marking or signaling from the switch. And as has been demonstrated time and time again, they can do it better if the switch can be told how to do it. You can do that in fixed function or in programmable, but if you want to experiment, you need something that's programmable. So the pressure is there. Is the pressure enough? The pressure is pretty high, and almost every cloud service provider that I've seen today runs some kind of non-standard network. How do they do that? By programming something. They change something or abuse something, right? If it's programmable, it's much easier to maintain, define, specify.
True.
And so I think that will come back on to the switch. It's a downturn. It's an economic downturn. The economic downturn goes away. You'll see the reemergence of programmable switches for sure.
I see. Okay, thank you.
Thank you.
Okay, a couple more questions.
Thanks for this explanation for the switch and NICs with IPUs. I would like to ask a question to Larry, if you accept. As SDN evangelists, we follow your content and believe in that this SDN is not only about data centers, but also campus networks, enterprise networks, because we have holistic picture and end-to-end, new protocol development, especially for cybersecurity purposes, as you mentioned, INT in network telemetry. How do you feel, or how do you think about this emphasizing on data center more with the NICs?
Emphasis. Well, I think they've been out in front, and they've showed us what's possible, and that's been hugely important. I mean, that's the history of SDN. How you bring that back into enterprises is a really, really good question. And I mean, the operation of the network is now in the hands of your sysadmin. You don't have an army of operators. That's not your business. And how we make these things easier to operate is absolutely the fundamental problem. And I come back to breaking the thing open. I'm going to turn this into a question, which is I'm 100% behind the notion you take a hammer to this closed bunch of magic and try to find out what's there. You break it apart, there's consolidation, P4 takes root, and now there's a retreat back into proprietary closed systems. And that actually occurs to me as a risk. I'm just wondering if you have any thoughts on where you see the biggest risks are going forward.
So the tension will always be between the vendor, who, whether they're a semiconductor vendor or they're a system vendor, who will be tempted to bake things in order to keep others out, right? And the buying power and the leverage that the equipment vendor has to stop that behavior, right? That's always there. That happens in the telco industry. You know, I'm probably familiar with Open RAN and things like this. It's the same debate, just with a different name, in breaking apart and has slightly different dynamics. But these things sort of happen again and again. And the cloud service providers, the hyperscalers, have the big leverage. They have the big pockets. They have, and the technical clout in order to be able to say, I want it that way. I want the interfaces there. So, you know, it naturally, that they were the pioneers of SDN, the first ones to define, to deploy at scale SDN, both in the United States and very significantly in China as well. And so the same thing will happen here. It will keep pushing and poking at the SmartNIC and the IPU, and it'll come back to the switch.
So PSA specs will continue to progress, and you will be more concentrated on
Yes.
DNA stuff.
Yes. So I think if you're a PhD student right now or a researcher right now, you know, hopefully you're not looking for something that's going to change the world, or expect something that will change the world in 2 years. That's what industry is there for. Look for something that's in the 5-7 years, a little bit over the horizon. Those beautiful ideas that Chang used to talk about that will actually change how people think. And if you can push us forward in this direction of programmable from end to end and programmable from top to bottom, that's the SDN control plane, and programmable from end to end. Imagine that you get to that point. There is a tipping point along there at which everything is programmable. And it completely will change how we think of networking into a programmable system, right? We are not there.
Yeah. As an ONF ambassador, I can say disaggregation and open AIs, right?
Yes.
Thank you.
Yeah.
So we are over, but I don't know what your time limits are, Nick.
I'm fine.
You're fine. Okay, keep going.
Well, hi, Nick. I'm
Hello.
He from Cornell. I have a question, which is, I think you already touched a bit on my question, which is, looking in we already have a lot of good applications, but looking in the next 10 years, do you see any fusion between the emerging technologies? Say now we're looking at autonomous cars arriving, large language models. Do you see a fusion between the P4 and programmable devices and those spark together?
Yeah, absolutely. And I think that there is a fabulous opportunity sitting right in front of us right now, whether it's from a commercial, from an industry point of view, or from a research point of view. And that is that it is very clear that a very substantial fraction of all compute that will take place, and all communication between devices will be part of training and inference. Right? And different people predict when the crossover will be and when it's larger than general purpose compute. They're different answers, so I don't know which is the right one. But it's sometime in the next few years. So imagine that you're doing training. You've got all of these values that are coming through that you want in some way to swivel, combine, right, in order to be able to bring those parameters back for the next iteration of training. There is so much potential there for modifying and training, whether it's in the NIC or whether it's in the switch. There is masses to be done there.
Thank you.
Thank you.
Hi, I'm Hari from Google. Question is about, so Barefoot did one thing right, which was we had a company that was actually on the forefront of defining a language that was meant for a switch type architecture where there was not much diversity in architecture. On the NIC side, there's a lot of diversity in architecture. There's the NPU style architecture, there's the vSwitch, type architecture. Unfortunately, in the open source, there isn't any backend that we can configure an architecture for. For instance, almost everybody realizes parsers in a similar fashion. So there isn't any backend compiler in the open source community that can be used to simply configure the parameters of the hardware rather than the I mean, like DPDK backend doesn't really have an architecture to it. It's just a piece of software.
Yeah.
How much do you think it would help if, in terms of velocity of development of these architectures and velocity of ideas that come into SmartNICs, if we had such a backend and if there was support for such a backend across vendors? And why do you think this doesn't exist?
So a couple of things. If I understood correctly, you really said two things. One is that the language is tied to a specific architecture, and the second one is that the back end is needed. I would actually say that those two statements are actually mutually exclusive. It's the fact that language is not tied to a particular architecture. It's a specification for a forwarding behavior that you want, right? And that you should be able to specify a forwarding behavior unambiguously, and many people do, and then deploy it in various other ways. There's P4 to DPDK, there's P4 to ePPF, there's P4 to a variety of different SmartNICs. Now, of course, in the early stages, as you're trying to figure out these, there will be some dependencies, of course. That's sort of inevitable. But let's not be too purist about this and say somehow it doesn't actually work. It clearly does work. It's actually happening, and it's happening in many deployments. The majority of P4 deployments today are not switches. So that tells us something. But in terms of your second question, right, which I think is a really, really pertinent and timely one, and that is, how do we get to the point where you can take from a specification and then compile it down and be able to see all of that magic? This was merely a case of the amount of money, of which you probably are aware, that was invested in creating that back-end compiler. I always used to say at Barefoot, the secret weapon was the compiler team, because it's the hardest part. It was the area where there was the most intellectual property. Having said that, it's just because it's difficult, it's not magic in the sense that if you know what the architecture is and that simple pipeline, and actually the pipeline was really simple, that simple pipeline and then mapping down onto it, it's a mapping problem down onto that pipeline. It is unfortunately and necessarily tied to the specifics, so it's hard to see what someone could get out of it in the time, but it's certainly been a topic of conversation.
So unfortunately, when we say that that there are a lot of SmartNICs being deployed using P4, in the SmartNIC community, the way P4 has been evolving has been vendors pushing their own externs.
Yeah.
Which defies the idea of portability of my P4 specification across multiple architectures. So having and picking a winning architecture and defining constraints for such an architecture, i.e. placement into different areas, what sort of a virtual architecture for a forwarding pipeline, right, would greatly help in, again, improving the velocity of.
Sure. I want to point and say that is there's a naive dream, right? Because there aren't any accelerators or brand of accelerators for which there is such a degree of abstraction that you can then have guaranteed performance, right? There aren't any. Right? So there must be some, and the trick is to be clever about making sure that's minimal, contained, and then if you're trying to port it from one to another, you know exactly what the task is, right? To think that we could come up with something that would work across all architectures and accelerate to the maximum extent, that's actually not going to happen anytime soon, right? Because we're still discovering through a good experiment in a variety of architectures for the NICs and the switches. That's wonderful, that's competition. And then over time, it will emerge probably, there will be one or two, and then you can make sure that you get easy portability. And this is the tension that's in the PSA and the PNA, right? And that's good tension, right? There should be that tension in there. But it would be, I think, too much to expect to say, oh, I shouldn't need to do any work to port and get exactly the same performance. That's where the competition comes from, that you want to encourage on the underneath. Otherwise, and this was the problem with OpenFlow, you're specifying a behavior for which there's no room for competition. You need competition, right, amongst the vendors. That's healthy.
Hey, Cyan here. Intel IPU X Barefoot have been on the P4 journey since last 6 years now. So what I have noticed is that vendors and users usually work on a P4 program, and after a point, the P4 programs usually come to a stable point, and it doesn't change that much. What does, however, change a lot is control plane functionalities and needs. And what I have noticed, I'm not sure if that is true for every device or not, like a lot of programmability usually moves from compile time to runtime. And do you see that as, I don't know, kind of a threat to P4 language in itself? Or follow-up question on that probably is that, do you see a probable evolutionary path of P4 in which, in addition to like specifying the data plane, we can also specify how the control plane functions and the APIs would look like?
So it's a very good question, that sort of partition between the two. If you're familiar with P4 runtime was very much about trying to do this, which was to allow flexibility and evolution in the API between the forwarding plane and the control plane, to allow that to evolve and change over time. They are trying to solve two different problems. You've got the forwarding behavior, for which my view, and happy to be proved wrong on this, my view would be you want something that is targeted at ease of use, ease of specification for forwarding behavior, for which you can have line rate, high performance behavior, whether it's in the NIC, the switch, or whatever the device happens to be. The control plane is likely to be in C++ or whatever it happens to have been developed in. And so it's at the interface between the two that you want the flexibility, so as that either changes, it can continue to evolve, ideally without bringing the system down. And with P4 runtime, that has been demonstrated, right? And so that has been demonstrated on a number of occasions, that you can actually evolve, expand, change the API between the control plane and the switch without necessarily bringing the switch down or bringing the control plane down, and expand it over time by giving you a schema for defining that interface. I do suspect that they will continue to be specified in different ways. That control plane will be specified in C++. But hey, if someone can come up with a really good way to do it, I'm happy to be proved wrong.
Hello, I have a couple of questions. So it's still not clear to me how much support on the software side we get for the Tofino 1 and 2 regarding roadmap for the compiler, or even tying with interesting thing that happened that we have on Intel Tofino for the couple 2 years, some IETF initial implementations for microseed or for path tracing. Do you see that still happening somewhere, maybe on Tofino, or moving to PNH somehow, or to IPUs?
So as hopefully you know, Intel, and I'm not really here to talk about Intel's products, but Intel has committed both publicly and privately to all customers their intent to continue to support indefinitely. There's no plans for end of life of Tofino 1 and Tofino 2, and that means the software too, and the support on the software. So there's not really anything more to it than that. And if you've got specific questions that are product related to a particular product, you do better to talk to those product engineers.
And the idea would be basically, if maybe on the IPU side we could emulate a limited switch to bridge the gap until we have new product lines that are capable of implementing this switch for these features.
Given that both ASIC and FPGA-based IPUs, both of them have P4 programmable pipelines in them, then you can generally run I'm sure not without exception, but you can generally run the same kind of protocols, the same kind of functionality into both, and so emulate the behavior of one on the other. So in principle, yes. Of course, as you know, with an accelerator, sometimes the specific features or specific resources are a little bit different, but in general, that's true.
Yeah, and lastly, I think that currently we have a lot of V1 model-based reference open applications.
Yeah.
And they're still trying to see when they're going to be ported to PSA. But on PNA, we are seeing a lot of momentum. So maybe
yeah, that's great. Yeah.
Okay, thank you.
Thank you.
Okay, we'll take these two more and then
Yeah.
wrap it up.
Hi, Nick. So I think I'm going to build up on something Rob asked first. In regards to being a renegade. So the ingredients you mentioned earlier, which is, there's a cabal of vendors who controlled implementations and how they get deployed. I have firsthand experience. I used to chair the Forces Working Group for years. And the reason it didn't go anywhere after 10 years was because the vendors didn't want to implement this. They're the only channels for, if something SDN was to be successful, then they own the boxes and the supply chain. So we failed. So I don't think you could have done anything differently. I think with you guys showing up with OpenFlow, that was a revolution to people like me, because you opened the boxes and other folks were able to implement. The second point I was going to make is in regards to the control plane. I do believe that the whole runtime thing may not be the best solution for a control plane versus data path separation. I think there's an opportunity there for schemas of some form. A lot of experience came from forces that could be put to play here. And the third thing, I just want to plug in P4TC, because you mentioned the idea of being able to do a split control pipeline, for example, where so P4TC is implemented in a way that you can split your pipeline in hardware and software. It's got access to the Linux kernel, which is a huge ecosystem opportunity. And you can essentially split across machines if you want it.
Yeah.
But there's still the control plan that needs to be written, of course.
As your question and your comments show, there is a massive opportunity and area for anybody who wants to innovate, improve, research, publish papers, do a PhD thesis on these topics. There are so many open questions, because we must go towards having a more programmable overall network system. Otherwise, frankly, those who are trying to build big networks are going to be so hamstrung by fixed functionality. We must go in this direction. So there are so many avenues to go, and many of the ones that you just described too.
Yeah.
Yeah, thank you.
Hi, this is Kentaro. I'm running P4 user group in Japan.
Yes, thank you.
My question is that understanding it's economically difficult to continue Tofino development, is it feasible or possible to open up the Tofino internal architecture like RISC-V does, and let the open community to kind of innovate the switch type P4 target?
Yeah. Hey, thanks for the question.
That's a great question.
Yeah, it's a very good question to ask, and one that we've pondered, right? And the pondering still continues, right? It's got little to do with actually holding on to anything, right? It's more actually the usability of what would be in other people's hands. Because when you've developed something for a while that has not been set up to be supported in an open source environment, RISC-V had the benefit of two communities. It had a large army of extremely capable PhD students at Berkeley and researchers who were all working as a large team funded externally, solely for that purpose of defining the architecture. And then on top of that, they had Sci-Fi, which is a company that is commercially running with that, and then further expanding that, right? So, there is a massive investment that is involved in doing that. So it's not something where you just say, oh, I'll just put it out there. That's not how it happened, right? And I've tried that before in various other projects, and it tends not to go very well, because people don't really know what to do with it. And then before you know, they're knocking on the door saying, well, I need support on this. You say, hey, it's open source. So you sort of need to create that ecosystem. Definitely open to ideas. But it's not obvious how to do it. But not fundamentally or philosophically opposed to doing that.
I see. Thank you.
Thank you.
That was great. Thanks for all the questions. Thank you, Nick, for all the answers.
Thank you for all you do. Thank you.